Okay, good afternoon, everyone. This is a rescheduled session of lecture series. So it was supposed to happen yesterday, but due to some unforeseen circumstances at the speaker's end, at Ankit's place, the weather was not well, so we had to schedule it today. So without wasting much time, I would ask Ankit to take over. He's presenting about SEM and EDS today. Ankit,
Hello, hello. Am I audible?
yes, you're audible, but throw noise in background.
Yeah, we'll try. One minute.
Better, better.
Hello. Now is it clear?
हाँ अभी better है. Yes.
Okay. So, good evening, all of you, and welcome to the method of surface analysis lecture series. So today we are going to talk about that scanning electron microscopy, which is by far the most popular tool for surface analysis. In scanning microscopy, we are obtaining an image by pixel. So that's where its name comes from. It's actually scanning the image. So it's obtaining the image pixel by pixel by gathering the information about each pixel at one time. We are not obtaining the whole image at once, but we are obtaining individual pixel at a time by scanning the image and drawing that. So first SEM was developed in 1938 and commercially it came into 1965. So from principle here I am trying to explain what are the three main phenomena which are going to happen in SEM or EDS. So here you can see when the primary electron beam hit on the surface of the sample, then several types of emissions have happened. Some are secondary electron emission, some are backscatter electrons, some are X-ray photons. So these three are main focus of study for today. So, so what's happened? If you are hitting the surface with the electron beam, you get some kind of signal. You get backscattered signal, which are electrons from primary beam, which encountered a collision in the first surface and are flying back from the surface. These are the backscattered electrons from the primary beam. You also get some secondary electrons, which are electrons belonging to the sample, which are knocked off their position by the primary beam. So what's actually happening when you hit the surface with the electron beam? Sometimes when the electron hit on the surface of the sample electrons, it fly back. That is called backscatter electrons. And sometimes what they cause the knocking of the electrons of the sample material. So that are called these secondary electrons. So, so what happens when these secondary electrons form? Then there will be a vacancy created in that electron shell of the element of the sample material. So for filling that electron energy, that electrons from the higher energy level come to that level, and during that process, they emit these X-ray photons, which is actually the equal to the difference of the energy from the higher energy level to the lower energy level from which the electron came to fill that vacancy. So this is the main basic what we are going to today study about this process. So what is the basic principle of the SEM? So in SEM, on the top of the on the top here you can see there is an electron source which is generally tungsten or lithium hexaboride, which are used to generate the electron beam. The beam is after that condensed using these condenser lens, and it generally works in conjunction with the condenser aperture to eliminate the high angle electrons from the beam. So after a beam passes through these condenser lens, it is more thin, tight, and coherent beam, which further passes through beam scanning system. These set of coils then scan or sweep the beam in a grid fashion, dwelling on a point for a period of time determined by the scanning speed. So after that, then there is a final objective lens. These objective lens uh, generally focus the scanning beam onto the part of the specimen desired. So when the beam strikes the sample, interaction occur inside the sample and are detected with various instruments. So here you can see there is a this BSE back scattered electron detector. Here is a X-ray detector, and this is a secondary electron detector. So all these detectors are present in the instrument, and we perform the analysis according to our need, what we actually want to analyze. Okay. So actually this imaging modes are two kinds in this SEM. First is the backscatter electron imaging mode, and this is the secondary electron imaging mode. So as I explained earlier, there is backscatter electrons are produced by the elastic interaction of the beam electrons with the nuclei of the atoms in the specimen. So they generally interact with the nuclei of the atoms, and they get reverse back or fly out of the sample. But in the secondary electrons are generally produced by inelastic interactions of high energy electrons with valence electrons of atoms in the specimen, which causes the ejection of electrons from the atom. So actually these secondary electrons are the electrons which are coming out of the atom. So generally this BSc is generally used for the analysis of the composition and topography, crystallography, and the magnetic field of the sample. But these secondary electrons are generally used for the inspection of the topography of the sample surface. So here you can see the example of these two kind of imaging mode. So what you actually get from this, see here it mainly focus on the this topography. It doesn't discriminate between the elements which are present on the surface. So it looks like a surface having a same element, but there is a this crater or depth are present on the surface of the sample. But in BSc here you see some light spots, some dark spots are present. So what actually it means? So in where these this dark spot there is some different material, and where there is some this light spot these are some different materials. So I can tell you one example in my case. So in my case I have a sample in which we perform the laser color marking, and after that for that color marking we heat the sample surface with the lasers. So during the process there is thin oxide films formed on the surface. So for analyzing that thin oxide films, what we have to do, we have to cut the sample from the cross section and then see in the perpendicular direction. So initially we were trying to get the idea about what is the thickness of that oxide films which formed due to the laser heating. But we are not getting clear idea, means because it looks like this secondary electron imaging mode. It's look like a almost constant surface. We don't able to discretize what is oxide, what is the main material. So after that, I came to know about that. Oh, for getting that oxide, we have to work in this BSc mode, in back scattered electron mode. So in the oxide region, the colors is completely different as compared to the normal material mode. So then we are able to discretize. Okay, this is the thickness of oxide layer, and this is my parent material. So that's the way. Means if you are only analyzing the surface of the sample, then it's always good to go with the secondary electron imaging mode, and generally people go with this only. But if you have a discretization or differentiation in the composition of the material throughout the surface, then it's better to get the go with this backscatter electron mode, so that you will able to differentiate. Okay, here it is something different. Here it is some different material is present. So here I am playing one video to give you more clear idea about whatever we have seen till now. Hello. Can anyone confirm whether they are able to see this video? Hello.
Yes, yes, it's
Yeah,
okay.
yeah,
I
we
can.
can see.
Okay, okay. Okay. Thanks. Hello. So previously you are seeing that that is secondary electron imaging, and now it is that backscatter electron imaging. So here you can see these are the images of obtaining from these different this imaging technique. So one thing I want to add that generally this scanning electron mode is of some nanometers only range, but these backscattered electron generally come out from the surface of some 100 nanometers or more than that, and even sometime if we have a high accelerating voltage it can go up to microns also. So it is a main difference between these also. So because in that this secondary electron we are trying to analyze the surface of the material, so it's very important that you go from the top of the surface only. There's no need to go in depth about the in the surface. But when you go about this backscatter, it gives some idea about your composition also, and uh, with this crystallography and magnetic field present in the material. So it goes somewhat below the this is the sample surface, top surface, and generally these backscattered electrons are very much of high energy, but these secondary electrons are low energy electrons. So actually, here it is a very clear when the primary electron came from the electron gun. So here you can see it hits the electron present in the inner shell of the sample material, and and it also get reflected back. So this is called the back scattered electron, and this is the our secondary electron. And after that, when the electron from the higher energy shell, say from L cell, comes to this K cell, then we emit one X-ray also. So this is the X-ray which generated after that electron came from that higher energy level to lower energy level, and this is the electron of the equal to the energy difference between these two. This difference between the energy level of these two shells. So the actually the complete video. So so now you got the clear idea of what's actually these three things are, and actually in understanding these three things are a very important thing for getting the idea of what is this SEM and ADS. So in SEM we operate in two modes. One is secondary electron mode, and another one is back scattered electron mode. And for ADS we generally analyze that X-ray which are generated from the this process. So basically, when so now we talk about this SEM mainly. So when we perform this SEM analysis, these six parameters are very important to get the clear, sharp image with a high resolution and without the loss of any information. That is very important thing in the case of SEM. Sometimes we get a very good image, but there is some loss of information. So first thing is this accelerating voltage. So accelerating voltage you have seen, uh, we apply to bombard the electron beam onto the surface. So what's happened when you increase that accelerating voltage very high, then the image is very smooth and of high resolution. But there will be some loss of the information, and that the charging effect will also come play in that, and there is a chances of damage of the electron beam, because that beam get sputter during that if there is a high this accelerating voltage. But if you decrease the voltage, then there is a you have to compromise between the resolution, but the structures are very clear. So here you can see the clear example of what's actually happening during that, uh, during increasing the voltage. So in this first image, you can see that the accelerating voltage is 20 kilowatt. So kilo electron volt. Here the image is very good, but what is actually this image is of? It is an image of a carbon foil on the top of the copper grid. But here you can see we are only able to see the copper grid. We are losing the what is present as a carbon foil. So image resolution is good, it looks nice, but there is a loss of information. We are not able to get the information about the what is the carbon foil present on the surface. But if we decrease the voltage, here you can see the foil is all present, but the image quality is very poor and its resolution is very low. So we have to make a compromise, and we have to select this accelerating voltage according to our need. Means what is up to what we are getting the information, and when we start losing the information. So it's a very important parameter in the case of SEM analysis. After that, there's a similarly beam current rules come into play. So beam current also plays a almost similar role, if the high beam current is there, then it is very hard to focus on the sample. But but and generally we our focus is that we generally try to reduce the beam current, but with the beam current reduction there is a one major problem. There is a uh, involvement of noise in the spectrum you are getting or the image you are getting. So if you decrease the beam current very low, then there's a problem of this noise present. So that's why FE, that field emission SEM, is very good, because in that we operate at a very low current and we get a very good resolution, high quality images. So this is a main problem with SEM also. Here if you increase the current, then it's very hard to focus, but if you decrease the current, beam current, then it's very there's so many unwanted signals you can also get in the image you captured. So another thing is uh, what is the beam resolution or the beam size. So as already we have studied in the laser course, it's very important to have a beam focus. Beam should be highly focused. So these actually all these things are linked to each other. Means what is a image resolution, what is a beam size, scanning area size. So for getting a good quality image, it is very important to control all these things. So say if we decrease the beam spot diameter, then what happens? Then we are able to get the very good uh, image with a high resolution, and the quality is also very good. But then your that scanning duration will increase. So that will increase the cost of the process. So it's like we have to settle in between what's actually we want to do. So for getting good quality image, we have to look into these parameters also. We have to play with the focal length. Actually, it is very important to place the sample exactly or approximately near to the focal length of the aperture. Otherwise, you get a very abrupt image or blurry image. And getting the narrowest beam possible, yeah, it is also very important. Beam should be very narrow, because and it should be generally close to the pixel size you require in the image. So if you say you need a pixel size of some 5 nanometer, then beam this spot diameter should also be in that range. Otherwise the two capture signals are actually overlap with each other, and you will get not a clear image of the sample you scanned. And then this I already told, there's a role of this beam current and the scanning rate. So all these parameters apart from that accelerating voltage and that beam current plays a very important roles during performing the SEM analysis. So actually these are some parameters you can see, these accelerating voltage, working distance, and this aperture size, that objective lens aperture size. So if you vary these, and you get if you are getting these thing, that spot size, sharpness, resolution, and what will be the quality of the signals we are getting. So it's like a complete overview. Means if you increase the this if your accelerating voltage is high, then sharpness is very good. uh, you get a very good sharp image, but there will be a loss of information, this surface info. So it's like you have to adjust in between what actually you need and what will be the optimum parameter for your analysis. So after getting the idea about the what are the main parameters, these are some aberrations present in during the CM analysis. So most of the things we have already seen that laser course which Deepak sir taught us. So there's a presence of this spherical aberration. So what it actually means there's a variation in the focal length depending on the this distance from the center. So here you can see that this spot has a minimum focal length, but if the multiple beams are coming, each have some shift in the focal length, different beams have. So here we have used different kind of correction lens and quadrupole to so that we get the focal length, this focal length for all these beams at a similar point. Then there is a presence of this chromatic aberration. So this is mainly because of the difference in the this different wavelengths. So if different wavelength light comes, then we also get there is a multiple focal point. It's not a single point, and it's get distributed over a range. So for that we try to get a monochromatic signal as much as possible. The beam should be close to a monochromatic one. And this was this astigmatism. This actually when we rotate the lens, so during that rotation of the lens to perform the scanning, there will be some difference in the focal length, and so that will also cause the variation in the image or the surface profile we obtained after the scanning. So we have to also correct this also using this some lenses are there, stigmator lenses are there, correction lenses are there. So we also have to consider all these aberrations which also comes into play during this SEM analysis. So after SEM analysis, what are the advantages and what are the drawbacks using this? So for the SEM, you have, I think most of us have already performed SEM analysis at any point of their research or previous work. Or if you have not performed in next 1 2 years, you will definitely perform this SEM analysis because it is a most basic analysis which everyone generally do. So if you have performed that answer, then you came to know that in SAM it's very less requirement of sample preparation, and if you have clean samples, generally we do some cleaning. Apart from that, we don't have to do anything else to perform the SAM analysis. And one thing is very important that the visual inspection of the surface. What it means actually, if you are getting some profile or some image of the scanned surface, so you can predict, okay, this kind of image we are requiring. So if you have went to this SAF facility in IIT Bombay, so first thing they ask, actually what you actually want to look in the sample, means what actually is your requirement from this SAM analysis. So if you give, okay, I want to analyze the laser scanning path or something, they try to get that, and their main focus is to get that, and then they set the parameters according to that so that we get our parameters according to our requirement. And here we also get some information about the composition using in this BSC mode, that backscatter electron mode. So you will also get some information about the composition. It's not actually quantitative analysis, but it will give you some qualitative results that, okay, here's a variation in the composition, and here it is this is a constant or a same composition throughout the scanned surface. And but the main problem with this is this getting the performing the analysis for these non-conductive samples. So here I am showing one non-conductive sample, some kind of microbacteria is there. So for performing these analysis on these kind of samples, we have to perform do the coatings, which I think Penal has also done when he has performed on some analysis, and I have also done this coating when I am doing the SEM analysis of iron oxides. So, and if you perform these coatings, then the resolution is of the SEM images will decrease. So that's one issue with this drawback with this SEM analysis. And one another main thing is if you want to get a good quality image, it's very important to optimize multiple parameters at a time, because there are so many parameters and each parameter plays a very different role during the analysis. So it is very important that whosoever is performing the analysis should have knowledge about these parameters and should select the optimal parameter according to the need of the according to our need of the analysis, means what we actually want to analyze. So this is very important thing in the SAM analysis. So when we have seen that SAM analysis, and in SAF facility in IIT Bombay, we have also this field emission also. So sometimes I also get confused why this FE SEM is more better than the that's normal SEM, or we call as a tungsten tungsten SEM. So or environmental SEM, which is a normal SEM. So both these equipments are almost same. Everything is same, but the only difference is come in the this electron generation system. So in these two different kind of microscopy, most of the setup is same. All the thing is good. similar, but there is a variation in the electron generation system, and because of that we get a very high resolution images using the this FESEM. So in the normal SEM, what we have, we get the electrons just by heating the tungsten filament or this lithium this lithium hexaboride filament. But in this FEG SEM, we get the electron beam after using that field emission gun. So what actually happened with this FEG SEM, we get a extremely highly focused and low energy electron beams. So beam is very narrow in the case of FEG SEM. That's why we get a very good resolution of images, and image quality is very awesome. And as I told already, that it is also capable of working at a very low potential. But you are getting all the things good, but here comes the catch, that the cost of this FEG SEM is almost 3 times, 2 to 3 times of that what is ESEM or the normal SEM. So here you can see this the source size. What is the source size? It is in some 30 to 100 micrometer. This tungsten filament has that spot size. But if you see this FEG SEM, it's less than 5 nanometers. So you can imagine how thin these filaments are for this FEG SEM. But here major thing is getting this vacuum. Here this vacuum required is 10 to the power minus 5, and here it is a very 10 very low vacuum, very not very low, very high vacuum is required during this FEG SEM. It is of order of 10 to the power minus 11 torr. So getting that vacuum, it requires some special equipment to create that kind of vacuum. So, and because of that, this cost of this FEG SEM is much higher as compared to normal tungsten SEM. So in ESEM and FEG SEM, there's only one difference. There is a difference of what is a electron generation system. And apart from that, all the things are same. We have similar that conduction system. We have same accelerating voltage. All the things are almost same. In that FEG SEM, also we have a similar two modes of operation, like a secondary electron mode and the backscatter electron mode. And in that also we get these X-rays. So you have seen that with FEG SEM, we also do this EDS analysis. With tungsten SEM, we also do this EDS analysis. So all the things are similar, but there is only variation in the what is the electron generation system. But in this EDS, what is there? Here we are not analyzing what are the electrons which are coming from out from the surface, but here we are analyzing this characteristic X-ray which are coming which are emitting during the process of electrons coming from the higher level to the lower energy level. Because in the lower energy level, that electron is knocked off because by this incident electron beam, and to fill that electron beam, this vacancy, electron from higher energy level comes to that, and during this process we emit this characteristic X-ray. So in EDS we have to actually analyze this X-rays to get the idea about the composition of the sample or the sample. So here you can see bombarding particles may create a vacancy of 4 energy levels of the atom. When vacancy is filled up with a higher band energy electron, the energy difference has to be released, and this energy difference is emitted as a X-ray photon. So this is a similar, and as you know, this hydrogen and helium have a only have an electron in the inner shell, single shell. In that case shell, it is not possible to get the characteristic X-ray from this hydrogen and helium. And even in the case of lithium, you get X-rays, but those X-rays are of very low energy level. So it's very tough to analyze that also in case of lithium. So and so apart from these materials, it gives idea about the composition of during this EDX analysis. So these are two types of X-rays we generally get. This is first one is Bremsstrahlung irradiation, and another one is this characteristic is X-ray irradiation. So these are this first one are generally continuous spectrum. These are always present in the whenever there is some bombardment of ion or electron any atom, we get these continuous spectrum of these X-rays. But these characteristic X-rays are actually uh, point of interest for us because it gives the peaks at a predefined energy levels, and by analyzing these energy level, these characteristic extras only, we get the idea about what is the composition of the sample. So actually we have not got into what is this EDS labeling. I have till now I have performed this EDS analysis so many times, but we never talk about this what is EDS labeling and what how it comes in the EDS spectrum. Because we generally operate in the that we generally get the signal of that K alpha lines only. But in some cases, it is very important to get the spectrum of these others lines also. So what's actually this labeling system is? I will try to explain that. So the peak is named after the cell on which the vacancy is formed. So think if that primary electron came into this K shell and it knocked the electron from this K shell. So we will first call is a K. K is the initial word. And if that vacancy is filled from the L shell electron, this is the L shell electron. So if that vacancy is filled by the L shell, then we call it as K alpha line, K alpha spectrum. But if that vacancy is filled from this M shell electron, then we call it as a this K beta line. So it is no, its nomenclature is like this. So if the electron, similarly, if the electron is knocked off from this L alpha, from this L shell, and its vacancy is filled from the M shell, then we will say that this is a L alpha one. So and if it is filled from that N shell electron, then we call it the L beta electron. So for the low atomic number materials, we generally get this K alpha only because there is not many electrons in some materials. There is no presence of electrons in this M shell, and generally we don't have any in whatever we have done analysis. We don't get electrons from this N shell because it's a very high atomic number materials. So, but in our analysis, whatever we get the spectra, we generally get the spectrum because of this K alpha. So, so here you can see that the K beta, what is that K beta? The electron is filled by the M shell is always photon energy is always higher than the K alpha. So that's was obvious because it is at a higher energy level. So if the electron come from there to K shell, we have a higher energy level of photon. But if it is filled by this L shell, then we have a lower photon uh, energy. We have a lower photon of lower energy. So this K beta photon is always higher than the K alpha photon energy, and M alpha is always lower than the M of K L alpha, which is in turn lower than that of K alpha. So as you know, during in the chemistry, the gap gets narrower as we increase from K to L to M and then N. So that's why we have a M alpha is always have a lower energy as compared to L alpha, and which is further lower than the K alpha. So this is a nomenclature which we use during this peak labeling. So these are the actually here I want to show that one spectrum of that in of that EDS spectra EDS analysis. So here you can say see that whatever I told till now. So here you say see that this is a Fe K alpha and this is Fe K beta. So here this energy level of this K beta is higher than that of K alpha, which is visible from this. And another point I want to tell that this here it is also present as a FeL alpha. Actually, this A is means alpha and B means beta. So here this you can see FeL alpha is lower than as case of K alpha. So these things are there. And one more thing is that whenever if you have done this ETS analysis, here we get the counts. So actually counts represent the number of it's actually represent the intensity of the signal which we received. So here you see this the K alpha signals are of higher intensity as compared to K beta. So it's actually not anything new. It's generally happen in this ratio that the K alpha intensity is 10 times that of K beta. So for number of photons which we get from that K alpha is almost 10 times that of K beta. It is a rule in this EDS analysis, so it always goes like that. And similarly for L alpha, L beta, you can see that it varies like this. So what's the actual device component in the EDS analysis? So most of the system is same in the case of EDS analysis. This is the primary beam system which we generally use of that SEM system. So there is no difference between the this primary beam system. But the major thing is in this is this X-ray detector. So this is a very important thing in the case of this EDS analysis. So, and apart from that, we have a pulse counter which counts the number of pulses and which we are getting from that X-ray photons. And then there's a processor which which counts these signals and draw the energy spectrum. So this processor is also very important. But this X-ray detector is further divided into several parts. So this is collimeter. Actually, collimeter means it's like an aperture which capture these X-ray photons. So collimeter is used to capture these X-ray photons. Apart from that, we have that electron trap. So sometimes we are capturing X-ray only, but with that some electrons will also come in that collimeter. So for that we have to remove these electrons from the signals which we are receiving. So for that we use this electron trap, which is only a kind of magnet which attracts these electrons and passes only the X-ray photons. After that we have a X-ray transparent mirror. So these mirrors role is to actually where we are receiving the signals and where we are analyzing it is some distance apart. So these are used to take the signals from the receiving point to the analysis point. And these semiconductor crystals are there. So semiconductor crystals mainly role is that to convert these X-ray photons into some electric pulse. So these are when these X-ray photons fall on these semiconductor crystals, we get some kind of electron hole pair which causes this what we can say the potential difference, and we get some kind of electric pulse signals from that. And we after that we amplify the system. And in this the most very important thing is that cooling system, which is very important because so many times so many unwanted signals also come. So it is mainly used to reduce the noise which generate during heating of the system. So when the system heats, then from that system also sometimes electrons come out. So that affects the results which we are getting. So this cooling system is very important in the case of this analysis. So here you can see that this is the ADS detector. So this complete thing is actually the cooling system. And here this small thing what you are seeing, this is the actually ADS detector. So generally in our campus we use that liquid nitrogen for performing the cooling. And in this EDS, this is a collimator assembly I told, which is like a aperture which captures the X-ray signals. And after that, here we have some magnet kind of system which captures removes the electrons which came with the photons, X-ray photons, and then from here it passes the these X-ray photons, and this is a semiconductor crystal which basically convert these X-ray photons into electric pulses. And after that we perform the this analysis. We have some processor which counts the these signals which are coming, and further they are some algorithms are developed to get the idea about the composition of these of the idea about the materials present in the sample, and using that we draw the some spectrum from the areas. So here you can see this kind of spectra we get after performing the ADS analysis. So in this we can do two type of analysis. We have a qualitative analysis and we have a quantitative analysis. So in my case, actually it is, if you have performed that, it is always said that this ADS spectrum is not that trustworthy to get the quantitative analysis of the material from the of the do the quantitative analysis, because in that there are so many things which affects the spectrum which are coming. But if you want to get the qualitative analysis, then it's a good one because it's a very fast and easy to use system. So and if you have to perform this quantitative analysis, you have to, there are so many correction factors which we have to take into account. So many times you have seen when you want to perform this ADS analysis, first thing they ask what actually material you are thinking present in the specimen, and after that only they will show the spectrum. So many times it happens, if I choose the carbon instead of oxygen, then all the spectra it shows that there is a presence of carbon. But if I choose the oxygen instead of carbon, then it shows that all the oxygen is present. So for the low atomic number, it's very tricky to get the quantitative analysis from the ADS spectra. But with two different samples, you can compare the results that, okay, in this the oxygen content is low, in this we have a high oxygen content. So ADS spectrum is better for performing the qualitative analysis. So what are the advantages and limitations of this ADS spectra? So this is very simple and not very expensive tool to get the composition, idea about the composition, as compared to other tools like XPS is there, which is very common, but it's very costly one. And major advantage that it is can be embedded with any existing system. So even you can use it with a TEM, with the SEM, ESEM or FEGSEM, or a that one analysis is there, AES, Auger Electron Spectroscopy. So with every analysis you can embed this EDS system and you will get the idea about the composition, some idea about the composition. And another thing is it is non-destructive method, so there won't be any um harm to the sample. It will remains as it is during this ETS analysis, and as I told, it's a very quick process and give a good qualitative analysis. And it also have this surface mapping capability. So here you can see that it actually, this is a sample surface, and here after performing the scan, it has shown that the different colors are here you can see the different colors are present, and what these colors represent, here you can see this is uh, written, this magnesium look like this, aluminum like this, silicon is like this. So it is also very it also has a capability of surface mapping, But as already told, there's some limitation, like it is very tricky to get the quantitative answer, and there's some need of reference samples, because so many times we have performed but results showed very abruptly, so there should be some reference before actually getting the idea about your sample. And this is very main issue, that batch sensitivity of light materials. So all these carbon, nitrogen, oxygen all look similar. So if you select nitrogen, you leave carbon, oxygen, it shows that all nitrogen is present. So this is also very critical in this EDS analysis. And surface resolution is also not that good, so it's cover as a whole. And it's also very much dependent upon the surface structure and relief. So these are some advantages and limitation of the process. So what we actually have studied in this lecture, we have tried to understand what is the basic working principle of these all these three different techniques, and how we diagnose these electrical signals which we get after performing the analysis, and what are the various parameters which are very important to control the received signals and get the results as your requirement, and what is the role of these parameters, means how these affect the results you are getting, and some examples of how the results received at different conditions. And basically we got some clear idea about what is difference between the normal or the conventional SEM and the FESEM and the ADS, and the limitation of these techniques and their advantages. So that's all from my side. Thank you for patiently listening.
A very, very thorough and detailed lecture by Ankit today. I think this is the benefit of research students presenting, giving talks and lectures. I think they can be very detailed oriented and they can include a lot of their recent experiences. So that is what Ankit did today, and he did it very, very well today. So we have around 7-8 minutes. Ankit, can you take up questions in the comment section?
Yeah, sure, sure. Thank you, Anu, for means. Okay, how deep from the so question is from Vishnu. How deep from the surface can we get the composition? Okay, so actually in this if you are performing this EDS analysis, so it's not actually sure up to what depth you can get, but in here you can see the image this. So here you can see that generally from the top surface we get these secondary electrons. After that we get the back scattered electron, and then we have this characteristic X-ray. So it generally goes up to 1 micron, also 2 microns, and you can vary this depth by changing the parameters as already told. So if you have a high accelerating voltage, these electron beam penetrate much deeper into the surface, and then you will get the idea about this composition at higher depth. But main thing is, Vishnu, I want to mention that these EDS are not that good to get the composition analysis. You can compare the results of some conditions of means different experiments, but if you need that exact results of composition, it's not to go. I will say that it's not better to go with this technique. You can prefer some other techniques are also there.
So it is good for only comparison.
Yeah, it's generally what I have seen. It's generally good for comparison only, qualitative analysis, and you can get idea about some microns. So even if they say they are performing this EDS analysis on the top of the surface, it's actually not on the top of surface. It starts getting signals from top up to some depth. If the accelerating voltage is very high, then it can go up to some microns also. So I have performed that analysis. That time I don't know about this, but now I know that it's not actually on the top of the surface. Okay.
Actually, that's
So
what I wanted to know. Like
yeah,
if
so
I
actually, if you want to get the idea in the depth of the surface, So what I recommend that you cut the sample, after that you analyze. So even at and you perform the line scan. So in that you will get clear idea about the up to what depth composition is varying, because throughout the line we have same composition. No?
Okay,
If we
so
cut
a
the
cross section analysis.
yeah cross
Cut and
sectional,
okay.
yeah. Then you have a much clear idea as compared to if you perform the analysis from the top surface.
Okay. Thank you.
Okay. I have experienced that with higher voltage we can go little deep in the serpent. What causes this? I have experience with that with high we can go little. Actually, with the higher voltage, I don't think we can go with the with if you increase the voltage now, it's a very clear thing. If you increase the voltage, then the beam will go much deeper, and its penetration power will also increase. So how you are saying that we go can go means actually Anup, I am not clear what you are saying that.
That is what I wanted to ask. Like with you also mentioned the presentation that with higher voltage the resolution gets better. Uh, the image becomes clearer and so. So
Hello, hello.
generally it is set at 5 electron volt now. Can you hear me?
Your voice is
Hello,
breaking. Hello, hello.
hello.
Yeah, yeah, no. What you are saying?
Hello, the network is not very good at my area. You can go ahead with the next question. We can discuss it later.
Okay, actually, I will try to answer that. If tell me if you get the idea. So, what I understood that if we increase the voltage, then we get a good resolution of images now. And what causes this? So, actually, what happens if you increase the this voltage? So, beam will be more focused, and it will be that diameter that there won't be much scattering happening on the beam during the when the that laser electron beam hit on the surface. Okay. So
Yes, yes,
it's a,
yes. I got
है
it.
ना? So then you
Oh,
get the clear images. That's why you get the clear images because one thing is very important that your pixel size, whatever the pixel resolution of the image and the beam focus diameter, that is spot size, should be in comparable. Otherwise, you won't get that. You have seen so many times we get very blurry images.
Ah,
So that's the issue because if we our beam spot size where it is hitting the surface, it is not exactly or comparable or less than the pixel size, then you won't get the clear idea about the what is the actual surface morphology is. Okay.
but generally the operators they don't provide you these details, right?
Yeah,
Or they?
they don't. I haven't listened these all these terms, and so many times what I have seen that if some TA is performing these experiments and you they are not able to get the image. So many times it happened with me. So they call the main that project staff, ma'am, this is the issue. So that ma'am will tell, okay, increase the working distance, decrease the aperture size, or increase the accelerating voltage, but they also actually don't know what's the reason behind
Hmm.
this.
Correct,
So
correct.
yeah, they just know, okay, we have to set this in this range, this range. So that's the main thing. Okay, Amit, to generate same image on workpiece of different materials. To generate same image on workpiece of different material composition, what parameter? Yeah, so actually, Amit, what I've told, actually, it's not a one parametric setting. I told actually in S whether you are performed SEM or ADS. Here you are talking about composition, but first thing is your beam should be focused and beam should be proper. Then you will get the proper this X-rays and the secondary electrons and the back scatter electrons. So it is very important. All the parameters, whatever I told in SEM, all these parameters plays a major role in whether you are performing SEM analysis or EDS analysis. So there's nothing difference in that part. All these things have to you have to control. After that, you will get the this EDS analysis. Okay. So you have to first control all the parameters what I told, that the accelerating voltage and the beam current, working diameter, focal length, all these are very critical for getting the whether you are getting the composition or the you are getting this surface morphology. Okay, so
Sorry to interrupt, Ankit.
hello,
Just
yeah.
we have completed 1 hour. Can you quickly wrap this up?
Yeah, yeah. Just one last
Yeah.
question is there from Prem. How does the
Yes.
apparatus differentiate between the secondary and back scatter electron? So Prem, there is no difference between the secondary and the back scattered electron apparatus. Here you can see, where's that image? See, here you can see that all the apparatus is same. They just have to change from whether they are getting the morphology from the BSC detector or this secondary electron detector. So they have to choose between this. It is not like the apparatus is different. All SEM have all these mode of operation, whether you are performing back scattering mode or secondary electron mode. So both these things are same. Just if you want that back scattered mode, you have to tell prior that I want this back scattered imaging mode on for my morphology analysis. That's the only difference, and all the equipment have same apparatus for the performing these two analysis. Okay, if anyone else have doubt, they can ask me later. I am happy to clear their doubts. I think time is up, so Anup, you can wrap up the session.
Okay. Thanks, Ankit, for this very detailed and thorough session on ACM. Okay, guys, we have completed 1 hour for the session, so we'll wrap this thing up and meet next week by 4:55 p.m. in events channel. Next week, speaker is Vishnu. So thanks, guys, for attending the talk. Thank you, everyone.
Okay, thank you all.